This video, we're going to talk about line of best fit. And a line of best fit is exactly what it sounds like. You're just taking a straight line, with a straight edge, a ruler, whatever you have, and you're just trying to position a straight line through a scatter plot the best you can make it fit. It's not going to go through every point. The line of best fit doesn't even have to go through one point on the scatter plot. All it is an estimate that gives you a reasonable example or a reasonable equation that you could use to evaluate the scatter plot with any value for x, or any number in the future that you might want to plug into your equation to figure out what's going to happen to the other variable in an estimating kind of way. So the toughest part with line of best fit is that it is an estimation. So there's not always one exact answer. There's more than one way to do it. And so that sometimes that gives us some trouble. Okay, so we're going to look at some vocabulary words here. We'll talk a little bit about what some of those words mean. And then we're just going to look at some example problems. And these problems will be ones that are similar to those that we're going to be looking at in class, and those that are in our books. Okay. All right, so to start off with our definition, a best fit line, or a line of best fit, is a straight line that matches the pattern of a set of paired data as closely as possible. So here we're talking about scatter plots where we have bivariate data, or we have two variables, and there's generally some type of correlation or association like we saw in the previous video, where if the trend of our points is going uphill, then we would say as one variable increases, the other variable increases. If the trend of our data is going downhill, then we would say as one variable increases, the other variable decreases. So all we're going to try to do here in this video is fit a line, a straight line, between the points the best we can. Another term that we need to know is called a residual. A residual, basically it's a fancy word that means how far away are all of your points from your line. So it's a vertical distance between a data point and a best fit line in a scatter plot. So the general idea here is that you want your residual number to be very low, because that means your line, your best fit line, is as close to the center of your group of data as possible. So if you look here, it says the line of best fit is linear. We've heard that word a lot this year, meaning that we can write the equation of the line in slope-intercept form. And remember, this is an estimation. So once we do this, there might be a couple different equations that we could get, but they should generally be the same slope and the same y-intercept, give or take a couple numbers here or there. And remember, slope-intercept form is y equals mx plus b. Okay, so here we have just an example of a scatter plot. I don't have any variables here. All we have is just an image of a scatter plot. And all my points here, those are my data. And so what I did is I went ahead and put in a best fit line. And sometimes it's harder when you're using a ruler, or maybe something that's not see-through. So some rulers that we use are clear, so it's really easy to position your ruler to be right directly in the middle, so that when you draw your line, your residual number is low. And so here's kind of what I did. I drew my line right here. It could probably be a little bit higher because you'd see some of these points up here are a little further away from the line than the points down here. Okay, so generally what we're trying to do is draw a line that the points above the line are the same distance away from the line as those points that are below. Give or take a little bit as we go, since it is an estimation. So to see my line of best fit here, and these are all my data points, and then this red line that I have connecting the data points to the line of best fit, that would be the residual. Okay, and this says you want this distance to be as small as possible. So however far each point is away from the line, you could actually add up all those distances, and that would give you your overall residual number. And like I said here, we want that to be a fairly low number. Okay, so that gives you an idea of what a line of best fit is and what residual means. And so now we're going to look at some practice questions from scatter plots and line of best fit. Okay, so we'll look at some questions from lesson 29 and some questions from lesson 30. All right, so question number 1 that we're going to look at here just gives us a multiple choice question. It says, which line is the best fit for the data? Okay, so here we've got 4 options. all we're trying to do is look at the line that is closely to the center of these data points as possible. So hopefully you can see here that option B would be our best answer here. Notice how my line of best fit is as close to the center of these data points as possible. Remember, the line of best fit doesn't have to go through any points. It happens to go through one right here, but it doesn't have to. But as you can see, this line of best fit fits the data better than any of those other three. Okay. All right, number 2 says, tell whether each statement is true or false. Letter A says, data points that lie above the trend line should be about the same distance as data points below the line. Well, we talked about that, and that was kind of where that residual word came in. And that means our distance, each point is away from the line of best fit. And we said we want that to be as small as possible. And one thing I also said was that we want the points that are above the line to be about the same distance away as those points that are below the line. So we would say true for that one. Okay, letter B. A line of best fit must go through at least one data point. We've said that a couple times already. That is false. Our line of best fit does not have to go through an actual point that's in our data set. We're trying to just fit the line as best as possible we can between all the points. Part C, a trend line is a good fit for the data if all of the data points are fairly close to it. And that's exactly what we're trying to do. We're trying to put a line in there that is as close to possible to being in the middle of all that data. So we'd say true for that one. Okay, letter D says a trend line must go through the origin. Well, all of our examples up here, we didn't have any of those examples that went through the origin. So we're going to go with false here on D. Okay, so the trend line does not have to go through the origin. All right, let's flip it over and see what we got here. Number 3 says, the scatter plot compares 10 daily high temperatures and the number of snow cones sold. John drew the following trend line to represent the data. So hopefully when you're looking at this, you can kind of see that our line, our slope should be a little steeper. Slope should be a little greater. Our line of best fit is a little off here. And Mary thinks there's a better trend line or a better line of best fit. And they want us to kind of figure out what's she thinking. Well, if you notice here, in the previous video, we talked about a point like this, that there's a name for that. We call that an outlier. Okay, so that point right there, it's part of our data set, but it doesn't really follow the same pattern as the rest of our data points. So when we're drawing a line of best fit, we don't have to take that outlier into account. All we have to do is use the points that are clustered together, and we could draw us a trend line that looks a little bit more like that. Okay, so Mary thinks there's a better trend line. We'd say that's our trend line right there. And what might she be thinking? She's probably thinking that we do not have to include the outlier. Okay, and so what that means is when we're drawing our line of best fit, we don't have to include that outlier to try and get our line of best fit as close to possible to the outlier and the rest of the data points, because that's not going to give us an accurate description or an accurate representation of what our data points are doing here. Okay. All right, number 4 says draw a trend line for each of the following scatter plots. If the data has no association, we can write no association. All right, well, scatter plot E here, F and G. So clearly F looks like it's going downhill, G looks like it's going uphill. So we're not supposed to write this here, we don't have to, but from talking about scatter plots, we could say this is a negative association, right? Or a negative correlation is another word you might hear. Okay, this one we could say it's going uphill, so we could say this is a positive correlation. Okay, so if you look here on E, there's really nothing going on here. The points are all scattered about. There's no really correlation, no pattern. So we could say no correlation or no association. Okay, so let's draw our lines here. We could say maybe somewhere around there would give us a good trend line, and possibly one right in there. Okay, all right, so let's look at some more questions here. All right, number 1 here, this comes from lesson 30, says the table and scatter plot show the total weight for quart containers of strawberries at Marty's Market. And they give us a table and a scatter plot. and it tells us that the points 3, 5.5, and 9, 13.5 lie on the line of best fit. Notice that these are not, well, let's check. They are actually part of our data set, right? But we said that our line doesn't necessarily have to go through any points that are on our scatter plot. In this case, the line does. It doesn't have to, but it can, all right? So now they want us to write the actual equation of the line. So here, all we're doing is we're writing slope-intercept form from 2 points. That's all we do. So we're trying to write y equals mx plus b, and we need to find m, and we need to find b. Well, m is our slope, and for our slope formula, we say m equals y2 minus y1 over x2 minus x1. That's going to help us find m. So we can label our points. We can say this is x1, y1, x2, y2. So we plug those in. We say m equals 13.5 minus 5.5 over 9 minus 3. Okay, so now we just solve that. 13.5 minus 5.5 gives us 8, and 9 minus 3 gives us 6. Okay, so that's our slope. So we could take this and plug it in right there. Well, we look at our options, and we don't see 8 over 6 as a slope. But if we could think, all right, we could reduce 8 over 6. Those are both even numbers. They could be divisible by 2. So this would translate or reduce to 4 over 3. So now we can look, this is 3/4, so it's not A. We got 4/3, 4/3, 4/3, okay? And then by looking at our graph, we could tell C is not right because this is our y-intercept. And our y-intercept, if it's minus 1.5, that means our line would be down here somewhere, right? So it's not C. And right here, our y-intercept is not listed, which means the y-intercept is 0, which means our line would go through the origin, and it does not. So that means B is our answer, okay? Well, if we didn't remember that, how could we solve that? How could we figure out what B is? Well, let's take our slope and plug it back in. So we have y equals 4/3 x plus b, and we're trying to figure out what b is. Well, we can take one of our points and plug it in the x and y values. Well, x is 3, y is 5.5. So we say 5.5 equals 4/3 times 3 plus b. Now we solve that. Well, 4/3 times 3, those 3's are going to cancel out. So now we're left with 5.5 equals 4 plus b. Subtract 4 from both sides, and we get 1.5 equals b, which is what we have right there, 1.5. So we know b is correct. All right, Yoshi chose A as the correct answer. How did he get that answer? Well, if you notice, our slope on A is 3/4. So probably what happened here is we accidentally found, well, not we, Yoshi accidentally did change in x over change in y. Instead of doing our slope formula, change in y divided by change in x. That's more than likely what happened there, okay? Number 2 says they want us to estimate the weight of 15 containers of strawberries at Marty's Market in problem 1. Well, we take a look at our equation. Our equation we solved was y equals 4/3 x plus 1.5. And they want us to find 15 containers of strawberries. Well, if we look here, number of containers is our x variable. So right here, we're going to plug in 15. So we'd say y equals 4/3 times 15 plus 1.5. So we get y equals, we could do 4 times 15 is 60. 60 divided by 3 gives us 20 plus 1.5. So the weight would be approximately 21.5 pounds. Okay. All right, so here we use our equation to estimate how much 15 pounds is going to be. So that's a big reason why we do write the equation of the line of best fit. It's because it gives us an opportunity to estimate what's going to happen in the future. Okay. All right, a couple more. Number 3 says, the scatter plot compares the number of mistakes that Kobe makes playing a song on his trumpet and the number of hours he practices the song. And then they show us a line of best fit. It says the equation of the line of best fit is y equals x plus 6. Well, This right here tells me my slope is 1 because this is like 1x, which means that's positive, which tells me my line should be going uphill. So we know this is false. The y-intercept is correct. It does start at 6. But our slope, actually, if we look here, we go down 1, right 1, 2. So our slope would be negative 1/2. So our equation should be y equals negative 1/2 x plus 6. So A is false. The slope means that you can expect the number of mistakes Kobe makes to decrease by 1 for every 1 hour increase in practice time. Okay, this is true, all right? And if you notice here, I made a mistake on my slope. Okay, so when we look at how our x and y coordinate, or our x and y axis are labeled or numbered, that's really important. Okay, so I counted just the lines here. I didn't take into account how the lines were numbered. So we went down 1, but we didn't go right 1, 2, because this is 1, right? This would be like a half. So this would not be negative 1/2 x. It would just be y equals negative x plus 6, which means our slope is negative 1. I apologize for that. All right, letter C says the y-intercept means that you can expect that even if Kobe does not practice, he would only make about 6 mistakes. Well, we would say true for that, because if we don't practice, that puts us at 0 hours of practice, and we see we have 6 mistakes right there, okay? All right, number 4, last question. It says the scatter plot compares the number of oranges remaining at a fruit stand to the amount of time that the stand has been open. So they want us to draw a line of best fit. They want us to write an equation to represent the line. And then they want us to figure out how many hours after opening would you predict that the fruit stand will sell out of oranges. All right, so we're doing quite a bit here. Well, if we draw a line of best fit, then we're trying to match our points here as closely as possible to our line of best fit. Okay, so something like that. So hopefully we can see that our slope should be negative because we're going downhill. So that helps us out a little bit. All right, and so now we're going to write an equation. Okay, so we need a couple points that our line passes through. And if we notice here, let's say 520. Looks like a good point there where my line is going through. And then 615. Okay, so let's do what we did earlier. We're trying to find the slope. So we have to say m equals y2 minus y1 over x2 minus x1. So we can call this x1, y1, x2, y2. So we get m equals 15 minus 20 over 6 minus 5. So we solve here, 15 minus 20 gives us negative 5, and 6 minus 5 is 1. So our slope is negative 5. So that's what we have so far. Y equals negative 5x. Okay, and we are estimating here. So a good thing for us to do, since we are estimating, is just look at where our graph starts on the y-axis. So it's not quite at 40. So it appears to be a little less than 40, maybe somewhere around 39. Okay, so let's say y equals negative 5x plus 39 as a good equation. Okay, so now it says how many hours after opening would you predict that the fruit stand will sell out of oranges? Well, if we look here at our hint, it says the oranges will sell out when y equals 0. So that's going to help us out a little bit. It says that number of oranges remaining, well, if we sell out, that means we don't have any oranges left. So now we could plug in 0 for y, and we could say 0 equals negative 5x plus 39, and we just solve for x. So we subtract 39, and we get negative 39 equals negative 5x. So we divide both sides by negative 5. So here we have a negative divided by a negative, so we know it's going to be a positive. So if we wanted to, we could just say 39 divided by 5. So we know 5 goes into 39 7 times. That gives us 35 with 4 remaining. And we could say add in a decimal here, decimal 0, bring that down, and we get 7.8. So approximately 7.8 hours after we open, 7.8 hours, or since we're estimating, we could say approximately 8 hours. So 8 hours after we open, or 8 hours after this fruit stand opens, we could predict that we will sell out of oranges. Okay, So that is line of best fit. So a couple things to remember. Just remember our line of best fit is a linear equation. So we get right in slope-intercept form. And the residual is the distance, the vertical distance from each point to the line of best fit. So that is line of best fit.